Hello, this is Mr. McCoy, and I am doing my first video lesson, and I'm starting off with a lesson on the law of conservation of energy. And basically, and specifically, we're going to talk about how to use an LOL diagram to keep track of all of our energy forms and what's going into the system, what's going out of the system, and whatnot. So let's go ahead and get started. Let's just do our first example. So our first example will be an initial state where we have a ball and it's a certain height, h, above the ground. And in the final state, we find that it has landed not on the ground, but on a spring. And it is, we'll call this h1, and then this becomes h2. And at this point, the velocity equals 0, and at this point, the velocity equals 0. Alright, so what we're going to do is we're going to do an LOL diagram, which is going to help us keep track of all of our energy forms and all the transfers into and out of the system. So the first thing I'm going to do is I'm going to draw an L, which is for the initial state. Then the O is our system picture, and then we'll have another L for the final state. So this will be for the initial, and this will be for the final. Alright, so we're going to start off with, down here will be all the energy forms we have. So we could have energy kinetic, energy gravitational, or maybe energy elastic. And then we have the similar ones over here, energy kinetic, energy gravitational, energy elastic. So, before we do anything else, we must properly define the system. So the system is whatever it is that we are looking at. So in this case, we have a couple of players. We have the ball, we have the earth, and we have the spring. So I'm going to start us off with the system of the ball plus earth plus spring. So it's going to be all the things in our system here. So basically, this becomes this basically makes us going to deal with a closed system, right? So there's nothing that's outside of our system. It's all incorporated within our system. So we look at our initial state and we say, all right, the kinetic energy comes from the velocity. Since we have no velocity, we're not going to have any kinetic energy to start. And then for gravitational energy, we look at height. And we see that in the initial state, it's a higher height, and here we have a lower height. So that means that we are going to have some higher gravitational energy here than we do here. It looks like, since I measured from the tabletop, that if I measure from the tabletop upward, that this right here is the lowest the ball gets. But this right here, this elevation, this is our 0 GPE. It's our lowest level at which gravitational potential energy would exist. We can't conceivably go below that at this point. So I'm going to assign some value for the gravitational energy for the initial state. Since it is at an H1, it's higher than H2, means we're going to have more here than we will here. Now how much we have is not really known. We don't have quantitative values for that yet, but we will in the future. So I'm just going to arbitrarily assign it 4 units. 4 blocks, if you will, of energy in the gravitational energy column. In the elastic energy column, there is none because there is a spring sitting down here, but it's at its full length and it has not been compressed at all before in the initial state. But in the final state, we find that it does compress, and it is in fact experiencing elastic energy because of that compression, deformation from its natural resting length, what they call the natural length. Now, if we go to the final situation, we notice that we're not quite at the 0, but we're definitely lower than we started here. So out of these 4 chunks that come from being this high off, I'm going to say I'm only going to have, let's say, maybe 1 chunk of gravitational energy in the final state. Then I also look at the spring. The spring is in my system, so it has been compressed. So I'm going to have some elastic energy. Question is, how much? Well, energy is conserved. So if I've got 4 units coming in, I should have 4 units coming out. If I allotted 1 for gravitational, I am going to need 3 units for elastic. And therefore, this equals this, and we have not broken the law of conservation of energy. Now, the next time I'm going to do this, I am going to change the system. I'm going to keep the same exact situation, but I'm going to change the system to something other than everything within it. So now I'm going to take my picture. I'm going to kind of put this aside for now, and I'm going to redraw my LOL diagram. So maybe what I could do is fold this over like that, and we'll still work with this same scenario. So we're not really changing the physicality of what's happening, but we're simply going to change our system. So now I want to change the system. The system now is going to be the ball plus the spring. No earth. So again, we draw the LOL diagram. We have our energy kinetic, energy gravitational, energy elastic, same way over here. So, if the system is the ball and the spring, there is no earth. That means there cannot be gravitational potential energy because the gravitational potential energy comes from the interaction between the ball and the earth. So, I am going to not have any kinetic because I'm not moving, not have any gravitational because I'm not interacting with the earth because there's no earth in my system, and the spring is totally relaxed. So I have no energy to start. In the final state, I have some elastic energy. Now before, we had 3 units. So I'm going to keep that going. I'm going to make this 3 units here of elastic energy. 1, 2, 3. So it looks like I started with nothing and ended up with 3. And that defies the law of conservation of energy. So the way we go about dealing with that is we must have energy transferred. We must have energy going into our system equal to 3 units here. So we end up having no energy gained or lost. We've gained energy in the system, yes, but we haven't really gotten it from a source that didn't have any to start off with. So we have 3 units coming in. 1, 2, 3. And this is done through a process called working. So this is done by work by what? What caused this to gain energy? It's got to be something that's outside the system. And what was outside the system was the earth. The earth itself pulled down with a force here due to gravity that caused it to move downward. And if the force is in the same direction as the ball moving, we know that it's going to accelerate and get faster, therefore giving the ball and the spring system energy. Let's try it one more time, but this time I'm going to try it for a new system, a system of the ball only. So again, we redraw our LOL diagram. And we have energy kinetic, energy gravitational, energy elastic. So we got all our energy forms again. Nothing's really changed there. I'm just resetting it all. I guess I should have done this before. All right, so now, if my system is the ball only, then I'm not allowed to have any kinetic because I'm not moving. There's no gravitational because I can't have gravity with just the ball. And there's no spring in my system. And so I go back to the final state, and again, there's no kinetic because I'm not moving, no earth, and there is no spring in my system at all. So I don't have any to start, don't have any to end, and some people would say, I am done. However, there has been some changes that took place. The ball has displaced, it has moved, the spring has been compressed. There are some things that have happened here, but the overall net change in energy is in fact 0. So we're going to have some work coming in. So this is work done coming in by the earth. And that's going to be equal to, I don't know, how much do we have before? That was 3 units. And then we're also going to have some work that comes out. We got to have the same amount of work that comes out. And this work is done by the spring. You see, well, why is the spring making energy leave? Well, the answer is with the forces. If I have a ball and the ball is coming in contact with the spring is pushing upward on the ball. As the ball moves down, the force on the ball by the spring is up. And if we know that we have our force is the opposite direction of our motion, we know that we are slowing down, and the way we interpret that now is it as losing energy. I hope that's been helpful, and we'll give you a few more examples as we go. Thank you very much, and have a good day.